So my name is Chris. I work for this tiny little company you might know. And the most important question of the whole conference, I would actually say, is who in this room has a Twitter account? Yeah. Well, it's actually not bad. I know that Ukraine is not very big on Twitter. You guys like Facebook a lot. I don't know why. So, but I work for Twitter, obviously. So I want you to tweet about the whole conference, right? I hope you did yesterday. I hope you attended a bunch of talks. You took pictures, tweeted about what you liked. Hopefully you didn't tweet about what you didn't like. You can. But if you're going to tweet about my talk, it would be nice if you add that hashtag, Twitter VM team, because Twitter actually has a VM team. And it's not so small anymore. We used to be only 4 people, but now we're 8. Ridiculous. We grow in size. And we do different things. So we have a bunch of people that are GC engineers. They deal with all the garbage collection issues that everyone has in the world, right, as well as we do. Then I'm a compiler engineer, so I do all the compiler stuff. A colleague of mine, Flavio, he's also working on the compiler. He's doing some Scala-specific optimizations for Graal. And then we have other people working on infrastructure, blah, blah, blah. And then something called Autotune, right? This is what this talk is about, Autotune. I will be talking about Autotune. If you don't know me, I'm working on the JVM for a long time, like 14 years or 15 now, I don't know. All these years, I was working on JIT compilers. So I'm going to ask you a bunch of questions because I'm not sure what do you guys know. You guys know what a JVM is? Yes? Okay. You know Hotspot? Yes, the JVM of OpenJDK. Who knows what a JIT compiler is? Oh, that's pretty good. Yeah. So for the people who don't know, it's a compiler in the JVM that compiles Java bytecode that you execute in the JVM to native code on the fly, like while you run your application, just in time. And like the other one would be ahead of time AOT, which like GCC, right? You would compile C++ ahead of time, then you get an executable and you run that one. But with the JVM, you compile while you run. So I'm working on JIT compilers. I used to work at Sun Microsystems and Oracle in the Hotspot compiler team, so I was working on Hotspot, mostly C2. Who knows what C1 and C2 are? All right, bunch of people. So Hotspot has 2 JIT compilers. One is called C1, or client compiler. The other one is called C2, or server compiler. You might have heard client and server before. You know the dash client, dash server that we used to use a bunch of years ago. Don't do that anymore. It's not required. C1 is a high throughput compiler. So it doesn't optimize too much. We just want to get away from interpreting Java bytecode to actually running on compiled native code. That's what C1 does. And C2 is a highly optimizing compiler. So it uses all the fancy optimizations that you can do in a compiler, like inlining, obviously, escape analysis, loop unrolling, and all these things. So I was working on C2. Pain in the ass. Yeah, really is. So that's why I keep talking about GraalVM. It's so much better. These are kind of the 3 biggest projects I've worked on during my time at Sun and Oracle. JSR 292, Invoke Dynamic. Some people might know it. Method handles, maybe you've used it. If you use Java and you use lambdas, you're actually using Invoke Dynamic under the hood. You might not know, but that's how it's implemented. So we implemented JSR 292. There were 2 implementations. One was a lot of handwritten assembly code, and that was in the JVM. It was kind of brittle, and we had to port it to all the architectures. It was very hard to maintain. We had a performance issue, and that led to actually re-implementing the whole thing in Java. So we took all the handwritten assembly code and moved the logic into Java, into a package called Java Lang Invoke that you might know. And I wrote a lot of that Java code. So if it doesn't work, you could technically blame me. But I always say, people touched the code after me and they broke it. My code was perfectly fine. JEP 243, Java level JVM compiler interface, JVM CI, we introduced in JDK 9. So basically what we did, next question. Who knows what Graal is? Not GraalVM. Good. 2 people know the difference. So GraalVM, Oracle made, announcements and blah, 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 so they do the marketing thing. It's unfortunately a little confusing because they use GraalVM as an umbrella term for 3 different technologies. And if someone tells you, oh, I'm running my code on Graal, you don't even know what that means. So there are 3 different things. One is Graal, the JIT compiler. Okay? Who knows what a JIT compiler is? Like, all hands should go up. I explained it earlier. Good. The other one is Truffle, which is a framework to implement language runtimes. And then the third one is called Substrate VM, which you might know under the name of native image. That's what everyone's excited about, the native image part. But when I say Graal, I only mean the JIT compiler. That's what we use at Twitter. Okay. So we took the interface that Graal is using. Graal is written in Java. And we took the interface that Graal was using to talk to the JVM and extracted it and made it a API. Right? It's not a supported API, but it's pretty stable. And we introduced it in 9, so 9, 10, 11, 12. All of these JDK releases have the same interface. You can take the same Graal version and run with it. Chap 295, we also introduced in JDK 9, which is ahead of time compilation. It's very different to what native image does. This one is basically a small command line utility where you can pass in class files or jar files, and then it sends off all the methods in that jar file to Graal. It compiles it, and then it spits out a shared library at the other end. And Hotspot can pick up that shared library when it starts up. It might help startup performance if you run a lot of code. If your application is very big, it might help you with startup. Now I work for Twitter, the best company on the planet. Forget about Facebook. It's a piece of shit. This is Twitter. That's what it looks like. We have hundreds of microservices and thousands of instances of these microservices. And we run on heterogeneous hardware, like everyone pretty much does. We own our own data centers, so we have our own machines. We have heterogeneous hardware. You guys run probably in the cloud. You don't even know what you're running on. But it's certainly not always the same architecture. Well, maybe the same architecture, but not the same machine. So this was in 2016, so it's already 3 years old, but probably more services now than there used to be. The big issue is, or problem is, performance optimization when you have that many different services. So you can hand tune, but it doesn't scale, right? You can only tune a few parameters because you have to build up a mental model in your head, and then it's difficult. It's very time-consuming, labor-intense, error-prone. The way usually performance tuning works is you sit at work and you think, this piece of shit is slow, I'm tuning it today, right? That happens every 3 years, 5 years, never, right? It's only when you get upset and annoyed that something not running as fast as you would like it to be. Then you would do performance tuning. The problem is upgrades make optimality fleeting. So we all live in an agile world and everyone fucking deploys to production 3 times or 10 times a day. We deploy multiple times a week, not 3 times a day, but multiple times a week for some of our service. So the code is constantly changing, which means that many services operate below optimality. It's certainly true for Twitter services, right? We don't tune all the time. You certainly don't do. Put your hand up if you do, like every day. No, probably not. So performance tuning, this is like a theoretical part a little bit. It's a function defined over domain X. You want to optimize over that domain X, and you want to find a configuration that maximizes F, whatever F is, right? F could be throughput, or you want to reduce CPU utilization, want to reduce latency, it could be anything. Reduce memory consumption, whatever. And it's always subject to some constraints. The number one constraint is it has to work, right? You will see later with the experiments I did that you actually can tune too far so that it doesn't work anymore. We'll see that actually. So this is performance tuning, right? You pick a few parameters, whatever, and then you run it on your system, you measure whatever you want to measure. Then you get the number back, and then a performance engineer, like an actual person, looks at that result and says, yes, this was better or not. and then that person decides what to do next. It's stupid to use a person here. It would be nice, maybe we could use a monkey, I don't know. But what we actually want is a black box. I don't want to know what that thing is. I really don't. It could be anything. I don't care. But I want it to tell me, yes, this was better or it was not. That's all we need to know, right? So what we use for this black box is something called Bayesian optimization. Anyone ever heard of it, Bayesian optimization? Very good. So when I'm going to explain Bayesian optimization, please don't say anything because I'm not an expert in this. So it's a method to learn potentially noisy objective functions iteratively, efficiently. That's important. We want to do it iteratively, right? We restart our services, and then we want to get a result pretty quickly, right? We don't want to like tune forever or run it forever until we actually have a result. It finds new optimum few iterations, what I just said, works well with nonlinear, multimodal, high-dimensional functions. That's important. The JVM has hundreds of parameters you could tune. You could throw it all in the Bayesian optimization thing. I gave this presentation, someone was asking me afterwards, can I tune my database with that? Of course you can. You can tune anything with Bayesian optimization. Tune your Minecraft or whatever you want to tune, I don't care. So as I said, I'm not an expert on this Bayesian optimization part. This is my colleague Rumke. He knows it very well. He has a very soothing voice, much better than mine. And he gave 2 talks about this. So if you're really interested how this all works, watch his talks. If you see the slides that he's using, basically what I did is I stole them. So here they are. I'm going to explain to you now very briefly what Bayesian optimization is, how it works, so then you can better understand later all the graphs and numbers we're seeing and how it works. So we're looking at one parameter, and it goes from -6 to 6. That's like the values, and y-axis is performance, high is better. These are 3 evaluation runs that we did. These are actual results. The actual performance curve looks like that. But we don't know that, right, at this point in time. So what Bayesian optimization does, it takes results and assumes a performance curve that looks like that. And then the blue area above the curve is the certainty that Bayesian optimization has that this is true, right? If it's the actual results we have, it's 0, right, because it knows. And this is overlaid with the actual curve. It looks completely different, but it doesn't matter. So what Bayesian optimization does, it takes the best result that it has, puts in a line basically, and then the blue part above the red line is the expected performance improvement at the bottom. That's the curve. That's the area of blue is down that graph. And so what it does, it takes the highest one and then does an experiment with that one. So it runs one, we take that one to the right, that's that result, and we take the one in the middle, it's that result, and we take the one on the left. So we run it, right, and we are going through our space, we take the one here, and then we've exhausted this space. And we can see above, with the results we have, these are the actual numbers, and that's what it looks like. So now we try it on the right, over there, that was bad. So we go over to the very left, we try that one, that was not as good. And so we try to find the global optimum that way. That's what Bayesian optimization does. That's really all. It's a stupid black box thing, but that's what it is. It's basically what a human would do, but it could do it faster. Good. We like it. We, Twitter, like it because it's non-parametric, robust, extensible, battle-tested on many types of real-world high-impact problems. That's important because we want this to work, right? We want actually a result that means something. The plan is with Autotune, and we are not there yet, believe me, the plan is to have Autotune always on in production. That's the ultimate goal, that the services are tuning themselves all the time. I don't know yet how long an experiment would run, maybe a month. It depends on the service really, and we kind of have to figure out what a good value is. So we need this to work. Good. That was the boring part, and now that's the fun part, experiments. So I ran a bunch of experiments. So what is Autotune? I want Boas to be a trending hashtag. I tried it at my last conference, didn't work, so maybe you can get it trending. It's Bayesian optimization as a service. So basically we have something called WetLab. It's a company we acquired a couple years ago, and it's an enhancement of something called Spearmint, which is an open source, still open source, you can get it from GitHub, open source Bayesian optimization framework. That's what we use, and it's running as a service inside of Twitter, right? And then we have Autotune, which is basically just a driver to run experiments. So we run in Aurora on Mesos, for example, but it could be anything. It could be Kubernetes or Docker or I don't know what, right? You just need something that starts and stops evaluation runs and gives you back whatever you're trying to figure out, right? Whatever you're measuring. And then Autotune is talking to the Bayesian optimization. Bayesian optimization goes through the whole graphy thing, gives you back the next value you should try for your next run. Very simple. That's all it does. Oops. Don't do that. That never happened. What is Graal? Who knows? I explained it earlier. Everyone should. Right. It's a Java virtual machine just-in-time compiler actively developed by Oracle Labs. You might notice there's an OpenJDK project called Graal, but most of the work is actually done on GitHub. So if you want to download it and run it and find a bug, go to GitHub. Uses JVM CI, what I said earlier, and it's written in Java, obviously. This part that it's written in Java is not really important for this talk, but if you want to try it, I have a talk that's called Graal, How to Use the New JVM JIT Compiler in Real Life, and that's still important because it's written in Java. And the way it works today, we're still not AOT compiling Graal, so you have to know a few things. Number one, C1 and C2 are written in C++, and Graal is written in Java, so memory allocation is very different, right? C2 would use malloc, and Graal uses, your Java heap. You should know this. If you're going to run benchmarks or anything, you should know about these things, because otherwise you're looking at the number the wrong way. So watch this talk if you're interested. Which parameters did I tune? Okay, these are the three that I tuned. I picked inlining-related parameters. Do people know what inlining is? Yeah, okay. So it's basically the complete opposite of refactoring, right? You have a method that you call from different places, right? You refactor it into a small method that you call from everywhere. What the compiler does then, it realizes, oh, this method is really called a lot. I'm going to take the code and just put it in the caller. That's what inlining is. It's a very powerful optimization. It's the mother of all optimizations, inlining. The reason why it's so powerful is because it makes your view of the world bigger. Like your compilation unit gets bigger, you know more. And certainly very important for something called escape analysis. I'm not going into details here with escape analysis, but what it does is it can get rid of memory allocations because it knows you don't need to allocate that memory, that object, if that makes sense. So I'm tuning inlining here to make the code faster and to enable more escape analysis optimization. So one is called trivial inlining size. It has a default value of 10. 10 means nodes in the compiler graph. So a compiler, what it does, it parses source code, or in our case, Java bytecode, and it builds up a graph, right? If that graph of that method has less than 10 nodes, we just inline it, because we know it's a very trivial method, and we always inline it without looking at any profiling data. Maximum inlining size is the other end of the spectrum, which if it's more than 300, we don't inline it. And small compiled low-level graph size is similar to the second one, but a compiler, most compilers that I know, have multiple levels of compiler graphs. High-level intermediate representation, low-level intermediate representation. One is high, the other one is low. That's how I explain things. You understand? High, low? No. So high means it's closer to the source code. In our case, Java bytecode. Low-level means it's closer to machine code. It could be ARM, could be Intel, whatever. That's the high and low. And it's also 300. It's very, very similar to the second one. So we are tuning these three. I had a talk at 2 years ago, I don't know, at Java Day Kiev was called back then, Twitter's quest for Holy Grail runtime. So it's basically, I tell the story of me working the first year at Twitter, how we started to run Twitter services on Graal. That's that talk if you're interested. What I did at this talk is exactly the thing I said earlier that you shouldn't be doing. I hand-tuned the shit. Stupid, but I did it because I wanted to know if it actually works, if we could tune it. So there are two metrics that we are looking at now and also later. One is I look at GC cycles. So I told you inlining and escape analysis can get rid of object allocations. That means if we can get rid of object allocations, we should see less GC cycles. That's actually what we're seeing. So it's a little convoluted, but like the red and the blue is C2, and then orange and green is Graal. So by just running this service, and this service is the tweet service, by just running the tweet service on Graal, we reduce GC cycles by 4.2%. It doesn't seem a lot, but remember, we're still doing the same amount of work, right? If we have 4% less GC cycles, that reduces, we don't have to do the GC, and it also reduces latency and all that stuff. So I hand-tuned it, the 3 parameters that you just saw, on a Friday afternoon for 3 hours. That was fun, a little bit. I could reduce it by an additional 1.5%, which I thought that's pretty cool. And then the other thing that's very important is user CPU time, CPU utilization. What we want to do at Twitter is reduce CPU utilization because that means we need to use less machines to serve the same number of tweet requests in that case. So by just running on Graal, we reduce CPU utilization by 13%, which is a lot. If you have any compiler engineers in here, if you ever done some compiler work, if you get 1%, you're happy. If you get 2%, you get home and get drunk because it's amazing. 13 is ridiculous. It's like a lottery win. So I hand-tuned it and got 2 additional % out of it, which I thought was pretty cool. And I was very proud of myself. But then Autotune kicked my ass, which you will see a little bit later. But 2%, I thought it's cool. So what I did for the parameters was I actually gave it ranges from where to where the Bayesian optimization should look. I did this for one reason, and the reason is I wanted the experiment to finish in a certain amount of time. Because what you actually want to do is you don't give it ranges, right? You say 1 to 1 million, or I don't care, right? Because the Bayesian optimization will figure it out anyway. If you tune too far, it will not work, it figured it out, but it will find the optimum anyway without giving it ranges. But I did this to fit the experiment on a slide, pretty much. Test setup. So I use a dedicated machine per instance configuration. It's very important. If you do performance benchmarking, performance evaluation of something where you expect like a 1 or 2% improvement, it's always in the noise. If you do this in your data center or in your cloud instances, you don't even know who else is running on the machine. And noisy neighbors can destroy all your performance evaluation. So I use dedicated machines, nothing else is running on them. All instances receive the exact same requests. Very important. Not only the same number of requests, but the exact same request. Think of the tweet service. It serves tweets. A tweet could be 1 character long or 280. Right? The memory allocation pattern would be very different. Exact same requests. We run with that JVM CI version, that Graal version, not very important. Default tiered C1 Graal setup. So basically, do people know what tiered compilation is? Yeah, I'll explain it really quick. So the JVM hotspot, you start out running your code and you're interpreting it, which is very slow. Then we compile with C1, and we run a native code, and C1 compiles it in a way that it collects profiling information. And then after a while, it uses that profiling information to recompile your code with C2, with the top tier compiler. And then you get your peak performance code. So basically what we do at Twitter, and what you can do in OpenJDK since JDK 10, is flip on a switch, and then you replace C2 with Graal in tiered. So you run interpreted C1 Graal. That's what we do. That's all we do. Experiment 1, the tweet service, my favorite one. It's a Finagle thrift service. So Finagle is like a framework that we open sourced. You can download it if you're interested in it. It's an extensible RPC system for the JVM used to construct high concurrency servers. I don't know what it is. I really don't, and I don't need to know. The important part here is that it's 92% Scala, so it's basically all Scala code. Almost all of our services are written in Scala, and Graal can deal really, really well with Scala code. So if you run Scala somewhere and you're not using Graal, you're stupid. That's all I'm saying. So the objective, what are we looking for? What are we trying to do? We try to reduce, you can see it here at the end, user CPU time. So I want to use less CPU. And if you remember, Bayesian optimization looks for a maxima, and we all know we're all software engineers, and we are very good at math. So what we do is 1 divided by, right? Because we want to reduce it. Constraints, as I mentioned earlier, I was only using 1 constraint, but we should actually be using more constraints. If we tune the individual services, you have SREs who take care of whatever services you have. They know exactly what their constraints are. They know exactly when the service doesn't work anymore, right? But in this particular case, the only thing I'm looking at is, as I said, we run in Aurora the throttle part. So if we get throttled in Aurora, that means we use too much CPU, and Aurora is not happy with what we're doing, and then it's not really running well. That's the only one I was using. If we're going to use this, as I said earlier, always on in production, we would use all the constraints that the SREs have. But for this slide experiment, it's perfectly fine. So that's it. That's 1 day, 24 hours of tweets. You can see it's going up and down, and then you see the slices, and the slices are 30-minute evaluation runs. They're not very long. The reason why I picked 30 minutes is, number one, I know the service really well. I know that in 30 minutes, everything's compiled, it's up and running, it's at a stable state. If we would do this for other services that I don't know, these need to be longer, right? Because we have no idea what the service does. And then the second reason is I wanted it to be done in 24 hours, the experiment, the Bayesian optimization thing. So 30-minute runs, blue experiment, orange control. As you can see, they can receive the same number of requests. That's the result of user CPU time. You can see the spikes. It's basically when the service restarts, and the spikes are JIT compilations, because it has to compile a bunch of code when it's starting up, and then it's running. If the blue line is below the orange one, that's an improvement. We use less CPU to do the same thing. And then what Autotune gives you is basically a web page, a table with the results. So it's sorted by objective, and it's 1.0838. That means we reduced CPU utilization by 8%, which is great, right? I, stupid human, could do 2%. Autotune, Bayesian optimization, 8. Very nice. Then 8.1, 6.4, 6.3, 5.8. So if, let's say the first two are maybe outliers, so we get probably a 6%-ish improvement, which is cool. You remember we had, we'll see it later, but we had like a 13% improvement just by using Graal, and an additional 6 now. That's the bottom of the table, and as you can see, there are actually 3 runs that violated the constraint. So it actually happens that if we tune these parameters, that the service doesn't work anymore. It really happened. Then we can look at the charts of the parameters we're tuning. Take this with a little bit of grain of salt, because we are tuning 3 parameters, so basically we're exploring a 3-dimensional space, right? It's very difficult to put this on a 2-dimensional slide. So every data point in a chart depends on 2 other values that are not the same, right? But we can see a trend at least. If you squint a little, you can see that it's actually trending upwards. And the default value for trivial inlining size is 10, if you remember. But what we really would need is like a 21, 22 number. So it's way too low, especially for this service. Then the next one is the maximum inlining size. It's kind of flattish, right? It doesn't really change a lot. there are the 2 points up there that might be outliers, or because it depends on 2 other values, it's just very good configurations. I don't know, doesn't matter. I don't need to know, really. And this is the last one. You don't even have to squint to see what the hell is going on here. The default for this one was 300, and what we really want is like 600, right? So this very much impacts performance. So the next thing I did was, I took the best result from the table that you've just seen and ran the tweet service for actually more than 24 hours, but I was running it with these parameters to see what is the real world impact of this configuration that we found. So we're looking at 3 different things: blue, C2, orange is Graal, default values, and then the red one is Graal with the parameters Autotune found for us. Okay, all the same, it's good. P is scavenge cycles, GC cycles, so the tweet service is using parallel GC, so we will look at scavenge cycles here, and by just running on Graal, it was like a 4.2 earlier, this particular run was 3.4% less GC cycles. That could be the 2 runs are a year apart, so the code might have changed, or it could be anything. So 3.4 here, and this is Autotune, and as you can see, that's already substantial. It's a 3.5% improvement. So Graal is really good, but if we tune it, we can double the improvement. It's like 7% less GC cycles. Very important for a service like the tweet service, because GC cycles always affect your latency. Yeah, that's the same number, just visualized differently. Maybe some people will understand this better. It's basically how much memory did we allocate to process one tweet. You can see it's pretty flat. It's going up and down a little bit because tweets can have different sizes, as I said. But it's the same number pretty much, 3.5, 3.47, right? Good. User CPU time. That's the one I care the most about, because it means we can get rid of a bunch of machines, and then we have less cost, and so on and so on. So in this particular run, it was 12% less by just running on Graal, and this is Autotune, which is an additional 6.2, which is roughly what I expected from the Autotune results, for a total of 18%. So that means that the tweet service, whatever it does, however many tweets it processes, not as many in the Ukraine as somewhere else, but because you're not using it, but we can use 18% less machines to serve the same amount of tweets, which is a lot of money. It's a lot of money. I wish I would get that money, but I don't get it. I've actually asked, but they don't give it to me. It's way more money than I make in a year. It really is. So if you're running something and you want to use 18% less of machines and money, that's the thing to do. The next thing I looked at was the latency of tweet requests, and I looked at P99 latencies. I didn't look at 3 nines or 4 nines, because if you look at 3 or 4 nines, you're basically only looking at the longest GC. If you look at 2 nines, you get a view how the world really looks like. So we certainly reduce latency by using Graal. It's a little hard to see how much it really is. This is Autotune. We can see it's better than regular Graal, but how much is it real? So what I did is I integrated over the whole 24 hours, and that graph looks like that. And then we can actually see how much it is. By just using Graal, we can reduce P99 latency by 20%. And if we tune it by another 8, it's ridiculous. So if you're going to look at Twitter, you get your tweets 28% faster. And if you're really fast reading, you could read 28% more tweets, if you know what I mean. That's really what I want, because that means our stock price goes up. So I did another experiment with a service called Social Graph, and I did 2, because the tweet service works really well with Graal, and it shows really good improvements in numbers. And Social Graph is like the tweet service, a finagle thrift service, so they're very similar. We basically use Netty and then finagle and then some logic on top. It's either the tweet service or the social graph service, right? And I wanted to see the difference between the two. So it's an abstraction for managing many-to-many relationships at Twitter, which means who are you following, who follows you. That's what social graph is. Good. You've seen this before, objective, just another name. We try to reduce user CPU time. We use the same constraint. Please don't get throttled. That's the result. Again, 30-minute evaluation runs, because it's very similar to the tweet service, and I know this service very well, as well as the tweet service. That's the result. We've seen that before. If the blue one is below the orange one, it's certainly better, and we can see that. And that's the table. The best result we have is 7.6, which is great. And then we have another 7.6, a 7.2, a 6.8. So I would guess maybe we get a 7% improvement. That would be nice. That's the bottom of the table. We had one evaluation run that violated the constraint. Ignore the 3 that are currently running. That's a bug. I hope we fixed it, actually, I don't know. These are the charts. So it looks similar to the tweet service, if you remember the first chart. Not as clear, though. And the default, again, is 10 here. And we found a 23. I think that's the best run. So 10 is not enough. And I want to argue that 10 is not enough for any code out there. But, you know. This one, similar to the tweet service, kind of flattish. There's a slight tendency going up. But as you can see, like, what is that, 400? So it's not really at the 500, like at the right end of the spectrum. This one, also trending upwards, not as clear as the tweet service. Like tweet service, you remember, it was like obvious. This one is trending. The important thing in here, if you might notice, is the range I gave it was 650. And the result we got is like 649. So I think that the range in this particular case was too small. I think it might even get a better result if we don't use the range. I actually ran this experiment later without ranges. I can't remember the result, but it's certainly doable. Good. So again, I did a verification experiment to figure out what's the real improvement. You've seen that before. The social graph service is using CMS, so we are looking at par news cycles here, and the reduction in cycles is only 1.6%. So that already shows that the code, whatever social graph is doing, is very different to what the tweet service does. We cannot get rid of so many object allocations as we could in the tweet service, so the reduction is not as big. This is Autotune, and the very interesting thing here is 3.5. So the improvement we get by Graal, sure, is nice, but you can twice as much by tuning it. It's ridiculous, right? We are all, including us at Twitter, throwing money out of the window because we don't tune our shit. And that's exactly that one. User CPU time, we can reduce user CPU time by 5.5, which is roughly like half what we can do of the tweet service. One reason why it's not as much as the tweet service is because if we can get rid of object allocations, our code gets tighter and we use less CPU to run our code, but also we do less GC cycles, which uses a lot of CPU. So since we cannot remove as much object allocations, we can also not reduce as much CPU time. This is Autotune, another 7.8. So we can get more out of Graal or the JVM by tuning it than just by using the compiler, up to a total of 13. One thing, some people might notice this, and I pointed out, and I don't have an answer for it because I haven't had time to look into it. But if you look at the difference between C2 and Graal, it's pretty much the same. It doesn't matter if the load is low or the load is high. But with Autotune, you see the improvement when the load is low is smaller than when it's high. I really don't know why. And the 7.8 is certainly when it was high, because I want to look good on stage. Right? So I'm not stupid in picking that one over here. So 13%. Any questions at this point? No? You all should have this question. right? Did I do the same Autotune experiment with C2? I'm standing up here and bragging about Graal, how cool it is. By the way, Oracle doesn't give me any money to do this. And I've also asked them many times they should give me some money, but they don't do it. Of course I did the same experiment with C2, because I'm not stupid. Someone would probably have asked in 30 minutes. So I tuned these 3 parameters, which are very similar to the 3 that I tuned for Graal. One is called max inline level, and Graal doesn't have that. So max inline level is how deep inlining goes, how many calls C2 is inlining. And it's when it has 9 calls, it stops inlining. Very important today, because everyone's using a trillion of frameworks, right? Framework A is calling this one, calling call. But then when you actually get to the code that you wrote, it stops inlining. Stupid. So that's 9. And we picked 9, 10, 15 years ago, which is certainly not enough today. Max inline size is pretty much the trivial inlining size. The only difference here is 35 means bytecode size. You remember Graal used nodes in the compiler graph? This is actual bytecode size. And if you've ever written code like in a small method and you put in some assert statements, and then suddenly your performance went to shit, it's because of this guy. Because C2 looks at the bytecode size and assert statements are in the bytecode and C2 doesn't, discount them. We never fixed it, I'm very sorry for this. Use Graal, that's all I'm saying. Inline small code 2000 is if we've already compiled the method that we want inline, and the code, the native code that we compiled is more than 2,000 bytes, we're not inlining the method. Like a stupid thing, I didn't put that in, I don't know who did. But it kind of makes sense. So the reasoning behind it is basically if it's 2,000, it's pretty big, right? So we don't want to inline it. But it's stupid to some degree because inlining can reduce the compiler graph a lot, and it could actually be better to do it. But anyway, it's there. Same thing, I gave it ranges for the same reason as I said earlier, to finish the whole run in a certain amount of time, and that's it. Again, I'm looking at the tweet service, and we have 30-minute evaluation runs, same thing, you've seen this before. These are the results, looks very similar, and that's the actual table of results. So the best one we have is 5.1. Which is great, like a 5% improvement with a compiler that everyone's using for ages. And just by tuning it a little bit, we reduce CPU time by 5%. Then we have a 3.8, a 3.5, and a 3.3. So I would argue the 5 is an outlier. So probably we get around the 3.5-ish% improvement, which is still great, right? If we can tune C2 and we get 3.5% less CPU. It's amazing. Autotune does exactly what it's supposed to do. But the difference between Graal and C2 is just too big, right? Remember, with Graal, we already get like a 12% improvement by just using it, and then another 18% compared to 3.5. So that's the bottom of the table. No constraints violated. Surprising to me, but yeah, whatever. These are the charts. So this one is very, very obvious, right? And you can see that's the max inline level thing I was talking about, right? How deep we inline. Default is 9, but it should be 16, 17, 18. That's really what it should be. And again, I'm arguing that 9 is not enough for today's code. It might have been enough 10 years ago, but today we have way more code, way more abstractions and frameworks and stuff, so this should be higher. This one actually surprised me a little bit because it doesn't really matter. It's like completely flat. We have this one, it's not really an outlier, but it's like one data point that's a little better than the others. It's really flat. And this one is also flat. So the big one that brings us all the improvements with C2 is basically how deep we inline. And that also means what I said at the very beginning, the more we inline, the bigger our worldview is, and then we can apply more optimizations to the code we have, to the compiler graph. I did not do an experiment, a verification experiment for this one, but I think it's probably 3.5. Summary of my talk, and it's the summary of all of my talks, and it's very simple. The reason why I'm doing all these talks is I want you to use Graal. I want you to try it. And the main reason why I want this is we need to test Graal better. I want it to become a more mature, stable compiler. It already is very stable, so everything I've shown you, and the tweet service, the social graph service, another service called, what is it called? The user service, and roughly 20 other services, like handpicked ones, the biggest ones we have, are running on Graal, 100% on Graal in production for 2 years now. So if you see a tweet, it's served to you by code compiled by Graal. And it just works. It never crashed. Did you lose any tweets? You don't know because you don't tweet. It's ridiculous. I'm talking my ass off here and everyone's on Facebook right now. So it's really stable. But what we want is like Oracle Labs is testing Graal all the time, but they only run, you can only run spec.gbb so many times. You will not find a new bug, right? When we started using Graal for our services, we found a handful of bugs. I explain all the bugs we found in the other talk, the Twitter's Quest for Holy Grail Runtime, if you're interested in that. And since then, that's more than 2 years ago, we haven't found a single bug, right? So what we want, the community, but particularly me, is that you run your shitty production code on Graal. That would be nice, because it finds all the corner cases, right? The older the code, the better. So if you can, pretty please, try to run on Graal. I'm sure you all run on JDK 11 in production today. Yeah, like we? No, we run on 8. Everyone's running on 8. So if you have a chance in some staging environment or whatever to run on 10 or later, that would be great, because then you only have to use that. It's the only thing you have to do. If you're still on 8, you can download a JDK 8 from Oracle Labs and try that. Please do this. I'm a very nice person, and I want you to save money as well. That's why I want you to try Graal. You could save money, right? It's like in our case, sure, it's the scale that we're at. We're saving certainly a lot of money, but the money you spend for your compute is usually a fraction of your revenue of your company, right? So if you're a small company with 3 employees, the $5,000 you spend per year on compute is still a lot, right? If you could save a little bit of that, that would be nice. If you can save, I don't know, $500 or $1,000 or so, that's an amazing Christmas party, Woo. And so please try this. Also, we reduce user CPU time, which means we use less machines, we use less electricity, we use less cooling in our data centers, which saves the world. That's really what I'm trying to do. I'm trying to save the world. And also, save some money on the side. That's also nice. And that's pretty much it. So if you can, on Monday, and you go to work, please try it out. And if you have an improvement, and I tell you, if you run Scala, you will see an improvement. If you're not seeing an improvement, you can sue me in court. I'll buy you 2 beers even, not 1, but 2 beers if you don't see an improvement. You will certainly, not certainly. You can also see an improvement for Java code. So we have a few services that are written in Java, and we've seen substantial improvements with them. With Java, it's like, I always say, it's a 50-50 chance if it's faster with Graal or not. The main reason for this is, and I used to work at Sun and Oracle on C2, not 1 day, 1 hour, or 1 minute we spend time on optimizing for other code than Java. Never. So if you run anything else than Java, I'm done in a second, please give it a try. And since she did that, I show you this. And I want you all, the people who didn't have a Twitter account, you should have created one by now, so you tweet about all this stuff and add that hashtag. Thank you very much. I guess I could take questions. One or two, or later. Yes, please. The guy in the back, or that guy.
Just a short question.
Sure.
So the figures you provided in the slides, all of them for the test environment, right? The enhancement figures, the percentage values.
The test environment. So when I did the verification experiments, right?
Yep.
So Autotune, yes, runs on the dedicated machines and everything, but the verification experiments were actually run in the data center with real-world production data.
Okay, so for the live environment, it's pretty the same as you just showed us.
Yes.
Okay.
It's like real-world savings. We have an internal webpage where I can go and see how much the tweet service costs per month, and we reduce that by that amount.
Okay, super, thanks.
Yep.
Hi, I have a question in regards, did you make any deeper investigation what actually Graal optimized, like for instance, if you write code in a style of a lot of usage of lambdas, will it be optimized, or actually, do you know what Graal could optimize and what could not from a point of view of source code? Is there some recommendation how to write source code to be optimized in Graal?
Right. So, yes, I have an idea. The thing that Graal does really well is inlining. It has a better inlining implementation than C2, and we've seen that. If you watch the Twitter's Quest for Holy Grail runtime talk, what I actually do is I disable escape analysis for both compilers, and then look at the performance improvement. And it's roughly half of what we see. So that means just inlining gives us half of the improvement. And then the other half is pretty much escape analysis. You were asking about how should you write your code? That was basically your question,
yeah,
roughly.
From that, yeah, roughly.
Roughly.
How
So,
should we write code to be better optimized in Graal?
right, so here is what I tell people. Write the code as it's supposed to be. Source code is meant for humans, right? You should understand it. Don't over-optimize in the source code. Don't do crazy shit. Yeah, you mean use a different algorithm if it's better than another one, but don't over-optimize things. What the compiler does is it's not an AI yet. It might be at some point, but what the compiler does, it's a pattern matching machine. So it matches patterns, and we look for certain patterns that we can optimize. And if you write your Java code or your Scala code or whatever Kotlin code as it's supposed to be, we can match these patterns. So write the code as you should. That's my recommendation.
Okay, thank you.
One more? No? All right, thank you very much.